Hello, and good day, everybody. We are once again meeting again on this platform just to look at our IEB 2018 paper. Right, so we've already done all the long questions on this very same exam, but I wanted to just take the time to answer the multiple choice sections. So, yeah, if you haven't subscribed, please just be part of the family. Please add to our numbers so that we can really get going. All right, and for those of you who need assistance with mathematics or physical science, please don't hesitate to just send us an email, and our email address is info@mlungisinkosi.co.za. All right, and yeah, for those of you who are actually writing the DBE exam, please don't be alarmed by the fact that we are looking at IEB. Essentially, it's physics is physics is physics. It's all the same thing, but nonetheless, the two exams are approached differently. But you would really benefit from this multiple choice section. All right, so enough with all the talking. Let's get into the questions and see how we can answer them and try to understand them, right? Okay, so the first question there, they say Newton's second law can be expressed mathematically as F net is equals to ma. Of course, we know that is Newton's second law, right? This consists of, all right, so they want to know in terms of vector quantities and scalar quantities. Remember that the force F net, that would be a vector quantity, right? It has to have magnitude and direction. Mass is, however, a scalar quantity, and acceleration is a vector quantity. So essentially, you've got two vectors and a scalar. So in this case, the correct answer there would be B. So for 1.1, okay, can you see our pen is trying to fail us now? All right, so for 1.1, our answer is B, right? And let's look at 1.2. So I was trying to mess around with it earlier on. So they said, so essentially we're given these two vectors, right? So they said the vector diagram shows two forces in the same plane acting on object O. Now, I just wanted to show quickly. So if you've got these two forces that are acting, now if you notice, they are actually tail to tail. So just to quickly show you how that works. So you've got this force in that diagram and another one in that direction rather. So that's 3 Newton force in that. Now, I want you to please note, if we were to find the net force in this, where would our, if we're pulling an object, where would it eventually go? Now, please note, you don't have a head to tail diagram, right? So please don't make the mistake of just drawing that F net in that direction. In this case, because you've got two objects that are tail to tail, right? You see they are connected by their tails there. What we would do is we would draw the net force first. And how would we get that net force? That net force, you can draw a parallelogram, and then from where it started, from where the tails start to the corner of your opposite end of your parallelogram, right? So that would be your net force. This is where your net force would go, right? Now, this is what I was trying to draw here. That would be the net force. But they say to you, another force, and by the way, that, if you were to calculate that net force, it would be 5 newtons, okay? For those of you who know the mathematics, of course, you'd use Pythagoras there, okay? And in this case, this is your 3, 4, 5 triangle, right? They say another force in the same plane as the other force is applied on object O. Which of the following represents the direction of the 5 Newton force must be applied to ensure that object O is in equilibrium? Of course, if object O was only or rather only had these two forces, it would move in that direction. But now we're trying to stop object O. We want it not to move anywhere. So what would we do? We must apply a force of the same magnitude as the net force, but only in the opposite direction. Okay, so it means that the force that would need to apply would be 5 newtons opposing that net force. So in this case, it means that our correct answer there should be B. All right, so I hope that makes sense to you. Right, let's move on. Let's go to the next question. All right, so now they give us a question on projectile motion, and I want you to please understand this. I'm going to take you through it. They say we've got a ball that is dropped vertically from rest, okay? They say from a hard horizontal surface, all right? They say the motion of the bouncing ball is represented by the velocity time graph as shown, and resistance is negligible. Right, so let's talk about this ball first of all. So in this case, I can see that it started from 0, so its initial velocity was 0, and it increased in speed as it went up, right? Rather as it went down, right? So in this case, you can, I just want to draw a space-time diagram, so that you see. So in this case, we dropped it, all right, from a horizontal surface. So in this case, it went down, okay? So there it is. It went down, and then it gets to the ground. Now, where did it get to the ground? At this point here. So in this case, this is when it arrived on the ground. Okay, the velocity is maximum here. And then at point A, this is where it touches the ground. Okay, this is when it was bouncing now. It touches the ground, but it immediately changes direction and it now goes up. So this would be B. B would be when it leaves the ground. Okay, so if I look at this, so there's A when it touches the ground. B is immediately after that when it leaves the ground, and it reaches a maximum velocity at C. So C would be the point where it reaches its maximum velocity, after the first bounce. And then what happens at D? At D, remember, after C, this is maximum height, the velocity is 0, and then it starts going down again, right? So essentially, it gets to the ground again. So B, or rather, let me rather say A, position, let me say rather B, which was the position when it, we said B is when it leaves the ground. Sorry, I incorrectly labeled this as B. That's why I'm confused now. So B is when it left the ground. C is when it reached its maximum height. And D is when it returns to the ground again, right? Okay, so I'm only going to focus on those. Of course, it bounces yet again at D. Okay, so it means it had another bounce on the ground. Of course, it did reach another maximum velocity and comes back again. So this is that position there, but we are only focused on this A, B, C, and D. Now they say, at which point labeled on the graph does the ball reach its maximum height after the first bounce? Of course, this was our first bounce, isn't it? So when does it reach its maximum height after the first bounce? That's at position C. So this is the maximum height after the first bounce. So our answer there should be position C. I hope that makes sense for you, right? Now we move on to the next one. They say we've got a speed boat. Okay, this is a very lovely drawing. I wish I could draw like that. They say a speedboat tows a water skier as shown in the diagram so that the skier accelerates, right? So they say the magnitude of the force exerted on the skier. So we want to know the magnitude of the force exerted on the skier by the tow rope is, okay? Now let's think about it. Okay, so let's look at the options that we're given. They say the magnitude of the force exerted by the rope is greater than the force, the total resistive forces acting on the skier. All right, I would accept that, okay, because they told us that the skier accelerates. So it does imply that the force that is pulling the skier must actually be greater than all the resistive forces. If there was wind there, if there's friction on the water, and so on, right? So in that case, that force must be greater. Okay, and secondly, they say is equal in magnitude to the force exerted by or on the rope by the skier. Now, I want you to please note this would be an extension, or rather an application of Newton's third law, right? And Newton's third law says if body A exerts a force on body B, then body B would exert an equal but opposite force on body A. Now, please, I want you to note they said the force exerted by the skier on the tow rope. So what would be the action-reaction pair there? It's the tow rope on the skier. So they said the magnitude of the force exerted on the tow rope by the skier should be equal in magnitude, right? And it's good that they qualified that it is magnitude. So I would actually take 1 and 2. So let's look at the third one. They say equal to the magnitude of the force causing the boat to accelerate. Right, remember those are two totally different objects, right? So in this case, the force that's exerted on this one is not necessarily the same as the force exerted on the skier, right? So as a result, that would not be true. So in this case, I would say, well, our answer, they say which of the above is correct. I would tend to go with 1 and 2. So in that case, that should be A. All right. I hope that you're still with me, right? As we move on to the next one. All right, so 1.5 simply says a block of weight W slides at a constant speed. Remember, okay, so they're telling us constant speed down a plane inclined at an angle theta to the horizontal, right? So remember, this guy is sliding down. Now they say to us the normal force acting on the block is N, so that's our normal force over there. And the magnitude, or rather in the frictional force between the block and the plane is F, so there's our friction. Of course, this is sliding down. Friction is opposing motion. So as a result, we know that friction would be up the incline, right? They say, what is the magnitude of F? So we want to know what is the magnitude of what? The frictional force there. Now you keep in mind that this object was actually moving downwards, right? So what is causing it to move downwards? It's actually the gravitational, the parallel component of gravity. And remember, how do we work out the parallel component of gravity? Well, remember we said what you simply can do is that you say, okay, so there you've got your weight there, or in this case your gravitational force. So you break that force, that weight, into components such that, so this is your weight, this is your perpendicular component of the weight, and this perpendicular component is actually in this particular case equal to that normal force. Okay, right? Remember, it's not accelerating in the perpendicular direction, but you also have the parallel component of weight, right? Which is, we'll say that's weight parallel there. Now please, I want you to note in this case the angle there should be theta, right? So remember, weight we normally have. So to get that parallel component of weight, and think about it, if we are talking about this object moving, it means that parallel component of weight is actually opposing, or rather it's the one that's causing it to slide down. But remember, friction is opposing. But if it's moving at a constant speed, it means this force F here, the frictional force, must actually be equal to the parallel component of the weight. Okay, I hope that makes sense to you, right? So in this particular case, what are we going to say? Well, how do we get the parallel component of weight? We normally say, well, or sometimes call it FG parallel. We say, well, this is going to be mg, which is the weight, the sine of the angle. Okay, why? Because it's opposite over the hypotenuse there. It's a 90-degree triangle, so it's opposite over hypotenuse. So in this case, we end up with mg, the sine of theta, or you can say w, the sine of theta. So in this case, I would go with D, So our answer for 1.5 is D. All right, let's go to 1.6 very swiftly, right? I hope that has been clear. So in this case, as we look at the next one, okay, so they say to us, we've got a ball of mass M that travels horizontally with a speed v that collides with a vertical wall. They say the wall rebounds at a speed v, okay, so it rebounds, so it was moving at v going that way, and it rebounds with a speed of v going in the opposite direction to its initial direction. They say, what is the magnitude of the change in momentum of the ball? Now, I just want to, park a little bit here, just to show it to you, how you would actually go about this question. Right now, I want you to think about it. So if you were to have, let's say, here's our ball, our wall here, and you've got a ball that's moving in that direction, right, with a speed v, and it rebounds with another speed v there. So to get the magnitude of the, of the momentum of the, rather the change in momentum, remember, you say, well, change in momentum is simply going to be the mass multiplied by the change in velocity, right? So this is going to be m. Now I want you to think about it. Remember that velocity is a vector quantity. So if we say, for argument's sake, we're going to now choose that direction as positive, then what would be that velocity there? It should be negative v, right? So you say, well, final velocity minus the initial velocity. In fact, let me write that down. Final velocity minus initial velocity. So it means I'm going to say mass. What is my final velocity? My final velocity is the velocity after it rebounds. In this case, that's going to be minus v, right? Minus, in this case, my initial velocity. So it would be subtract that with a positive v, okay? So this is minus a positive v, which would make it minus v as well. So what do you get? You get minus 2v there, okay? So it means it would be minus 2mv. And it's showing you that the change in momentum is actually in the opposite direction, okay? So in this case, because they were looking for the magnitude of it, it means that we are just talking about 2mv, and our answer is D, okay? Right, I hope that that makes sense to you. Right, as we move on to the other one, I'm just going to cover this portion up. I'm going to just continue over this side. I'm in need of some space there, so I'm trying to create some space. Right, okay, so in the next question, we've got a stationary nucleus, okay, that decays and emits an alpha particle of mass m, okay. They say the alpha particle is emitted with a momentum of p, right, and kinetic energy E. They say the mass of the recoiling nucleus is 50 times greater than the mass of the alpha particle, okay. So remember, this guy is 50 times, right, the mass of the alpha particle. Right, now they ask us the question, right, what are the magnitudes of the momentum and kinetic energy of the recoiling nucleus? Okay, right. So the momentum of the alpha particle, right, they had given us that as p. But remember, the stationary nucleus, and remember they said that it was stationary. So what that means that, remember, the sum of their momentas before collision would be equal to the sum of their momentas after collision, okay? So I want you to just think about it. Remember, both of them were combined at that point, okay? So it means that the total momentum was what? 0, right? Before, but then after the event, both the recoiling nucleus as well as the alpha particle, right, now they are now going apart, right? So they told us, so it's going to be the momentum of the, okay, I'm just going to say recoiling nucleus plus the momentum of the alpha particle, right? just going to call it AP if you don't mind, right? So now what I'm going to do is say, okay, but I know that the total momentum should be 0. They told me that the momentum of the alpha particle was P, all right? So in order for me to have 0 on this side, what should be the momentum of the, of the recoiling nucleus? Of course, it should be minus P, right? So that minus P plus P should actually give me my momentum afterwards. So it means that the momentum of the recoiling nucleus must also be P, right? I hope that makes sense. All right, now let's talk about the kinetic energy. Remember, they said the kinetic energy of the alpha particle, right, is E. And remember that the mass of the alpha particle was, was mass m, right? So in this case, because they didn't tell us about, now I'm going to actually put this way. This is half mv squared, right? So I want you to think about the momentum, or rather the kinetic energy as half. In a way, I'm just simply going to say it's half of this is mv times v. Okay, I want you to think about it that way, right? So E would be half of mv times v. But what is this? This is already the momentum, and we know that the momentas are the same, right? Okay, so in this case, I can simply say this is half of P multiplied by V, isn't it? Okay, so this was given as our momentum. Now, let's talk about the recoiling nucleus, okay? In fact, maybe I shouldn't have done that. I shouldn't have done that because I need that mass m there. Okay, so I'll just leave this as mass m. But now what would be the kinetic energy of the recoiling nucleus if its mass, okay, is 50 times? Now I want you to think about it, okay? If their momentas are to be the same, okay, let's take the alpha particle. So let's take the momentum of the alpha particle. So the momentum is P, and the mass is m, and the velocity is v, right? But if I'm to have the same momentum P also for the for the recoiling nucleus, remember the mass is 50 m, right? But then what should be the velocity of the of the recoiling nucleus, right? In order for the alpha particle, to have the same momentum, so I want this to actually be equal to mv as well. So it means that my v should actually be v over 50. Okay, I hope that makes sense to you. So if I multiply this and that, so what does it give me? It would be 50 divided by 50, which would be 1, and we actually end up with mv as well. Okay, so I want to illustrate this here, so that it means if the mass is 50 times, then it means its velocity should be 50 times smaller, so that it could have the same momentum, right? So as a result, it would mean that the kinetic energy should also be 50 times smaller. So I would actually go with, so for 1.7, I would actually go with B as my final answer. Okay, right, sorry about that. I keep trying to move this thing so that I can explain it to you better. Right, so my answer there is 1.7. That should be B. All right, I hope I've tried to explain it in a way that would make sense. Right, as we move to the next question. Right, so in 1.8, they say a small charge Q is placed in an electrical field of a large charge Q. Both experience a force F. Of course, they are going to exert forces on each other. Right, now they say, what is the correct expression for the magnitude of the electric field of charge Q at the position of small charge Q, right? Now remember, we want the field of charge Q, right? Now remember that when you calculate electric field, we would actually represent Q as a sort of a point charge, as something that doesn't exist. Q experiences a field due to the other charge Q, small q, right? So in order for me to actually express the electric field, I would say, well, E for this, remember we've taken this as a point, right? So it would be the force that they exert on each other divided by the charge that Q, small q. So it would be F over Q, because remember we are taking the charge of the other, the charge of the other charge, hope you understand what I'm trying to say, right? So in this case, we're saying you would take big Q as a point because we are looking for the field on charge Q. So you take charge Q as a point, so it means that it will be a field that it experiences due to the other charge, which is small q. And similarly, if you wanted the field of small charge Q, of course it would be the force divided by the big charge Q, right? So the correct answer there should be D, right? So it means that for 1.8, our answer, our answer should be D. All right, now let's get to the conclusion. We're at 1.9. They say an ideal emitter is used to measure the current in a conductor. Which of the following describes the resistance of an ideal emitter and the way the emitter and the way the emitter is connected to the conductor? Now please remember, ladies and gents, when we talk about an ideal emitter should always have zero resistance. In fact, I explained that. For those of you who haven't watched my series on circuits, please go and watch that. Okay, and in this case, it must always be connected in series so that it allows all the current to flow. All the current that flows through the emitter must flow through the rest of the circuit. So our answer to that should be A, which in this case is zero resistance, and it should be connected in series. If it can be connected in parallel, remember all the current would bypass all the other components of the external circuit, and as a result you'd end up having a short circuit taking place there, right? Okay, quickly as we reach the end, so that's 1.10. They say a coil and a magnet can move horizontally to the left or to the right simultaneously at the same speed. They say, in which of the following will conventional current, okay, note conventional current, okay, be induced in the coil in the direction as shown in the diagram, okay, when both magnitude and the coil are moving, right? Now, please, I want you to note, when we apply the law of electromagnetism, we always look at moving the magnet, okay? If we are moving the magnet from north to, it must be in such a way that it opposes the direction of the magnetic field. Remember that the magnetic field is always moving from north to south. So if I were to move the magnet in that direction, right? So it means that the coil, right? So think about it. So I'm moving the magnet to the right, okay, in the opposite direction to the magnetic field, right? In this case, the coil would move in the opposite direction, okay, right? So in this case, because I want the current to follow conventional current, right? So in this case, I would say I'd move it to the right, okay? And in this case, it means that my coil should move to the left. And so my answer to that question should be D. Okay, so I think we reached our conclusion in that. Okay, sorry about I kept on moving because my explanation is so animated. I keep moving the thing around. Okay, so we've reached the end. So those are all our answers. I hope that you were able to understand that. And please, ladies and gents, continue to invite others as we try to look at physics and try to make it as simple as possible so that you can, score big marks for those exams. Okay. And for those of you who are writing the IEB exams, all the best for your exams in the near future. And for those of you who will be writing the DBE exams, please continue working hard and make sure that you understand as much as possible. Otherwise, from me for now, I will see you guys next time. Sharp, sharp.